So good morning. I hope I am audible.
Yes, sir, you're audible.
Okay. So we shall continue from where we stopped. Okay. So we were trying to see the methods for data-driven model development. Okay. And we have seen various methods. For instance, first one was linear regression. Okay. Or any sort of regression. Then if you have an empirical model which is, let's say, first order plus time delay also, how do you fit it from the data? Okay, the first was first order only. Then we have seen what is first order plus time delay. So then we have seen the second order system. Okay. Then we have seen the neural net. So now,
So before we start the CADs, I just had a small query from the class
go ahead.
uh,
Yes.
regarding the class work. Here, the minors were of
What is
30 weightage, as well as the quizzes were of 15 weightage per quiz, like best 2 of 3 amongst 30 marks. So why are we reducing
yeah?
the marks per evaluation?
No, there is not evaluation. So the exam is for 20 marks. You can scale it up to 30.
Uh, okay, so is that planned that you'll be scaling it up?
How can it be otherwise? Minor, if the exam is for 20 mark and the weightage is 30 marks, you invariably have to scale, right?
No, sir, we thought that you might be thinking of a minor too, so just wanted to
You
tell.
might did not. I did not hear.
I
Hello.
thought that you were thinking of another minor. That's why you were saving up 20.
No, there is no minor. Only one minor because as
So
part of the overall
you'll be
system,
scaling up for this.
no. So see, what is the minor percentage? 30%. The exam was the exam was 20 marks, right? One is
Right.
percentage and one is marks. So what does that mean? So this 20%, this 20 marks highest should corresponding to 30% of 100. Very simple math, right?
It is simple, probably, sir. Like we haven't had a scale up yet, so
Wouldn't
the scale up actually
no see,
disturbs
it's
something.
up to us. No, I don't think it disturbs anything. So 20 mark people who got 20 marks would be getting the 30 marks, and well, that's all about it. So see, so first your what you call the contribution. So the percentage is the overall contribution to the 100%. Correct. Exam you can even do it for 10 marks. Correct. How it's going to be different?
I
I
mean,
don't
sir,
see
having
anything.
a 30 marks, so it gives more chance of scoring more. So that's the only case. I mean, the percentage is maybe not the right
No, so
mechanism.
see, and all,
Maybe
yeah. So, yeah. Pardon?
I mean, percentage might not be the most appropriate method of upscaling. We might rework it if we have certain more evaluation added to it, that we have a mark to mark.
No. There is no more evaluation. Minor is done, and minor marks is evaluated out of 20, which would be evaluated totally out of 30. This is not for the first time, I guess you are seeing this business. So if there are 4 assignments and it total up to 20, how do we do it?
In general, we do 5 each, but those assignments carry 5 each. I mean, it's not like they are there 3 and then
So
we.
sometimes that's all. So you know, I think so. The total marks has no bearing on the percentage contribution, no. So let's say if I conduct an exam for 30 marks major, what will you do? The 30 marks corresponding to your 40%. There are two things, right? One is contribution and one is the total marks. And I don't see any sort of problem out of this.
I mean, sir, what we've observed over the years for us is that we've had downscaling, but upscaling has had a lot of repercussions for the students who scored less. That's the only point. Like we had it in CLL 110 back in semester 3, so it actually disturbed the entire gradings. That's the only point.
Yeah, but I think this is the way it's going to happen. So if you are not clear about it, I think I'm making it clear at the moment.
Okay, sir.
Okay.
Yeah.
Okay. So let me just get restarted. Okay, so I just lost the train of thought. So, okay, so yeah, so eventually, what are we doing with this data-driven models or any model? So, one is, of course, use them for control. So let me just. Okay, so eventually, what will you do this model? So, we have models, okay. So, models now we have seen that it could be obtained either from first principles or from data. Okay, so our eventual aim is, of course, use them for control. You can also do a model that is developed first principle. Of course, you will have to maybe simplify, which we have seen. Or you have, if you have complex model, you uh, uh, kind of combine them together. Okay, then either you or use the other rule. So this is coming from physics. This is coming from data. So in industry, there are two broader applications for each of these. Okay, so the broader application in the sense that uh, either you use them for control, of course, which we will see how do we use it, fine, or you may use them just for observation, which you call it as soft sensing. Okay, so what do you mean by soft sensing? Okay, so uh, so, for instance, let's say you are working on the for a what you call a distillation column. Okay, and there is feed coming in. Okay, and there is distillate, there is condenser, there's distillate going back. Okay, there's a splitter out here. Fine, there is a what you call a recycle. So this is a reboiler. So this is your distillation column. This is the distillate. This is the feed. This is the reflux, and this is the reboiler. And you have various trays inside of this. So what is that you are? What is that is happening? Okay, um, and your parameter of interest in most of our process operation would be most parameter of most interest. What of the process operation would be purity. Okay, and it could be concentration because the final product spec. So you cannot have a temperature as a product spec because it is most of our production would have quality specs. So be it a diesel, be it a petrol. So you know what is the percentage of the hydrocarbon chain if it is and what you call what is octane number, cetane number. So these are all what you call production specifications. Okay, and which are okay. So so for it could be if it is a pharma, it is a pharma or pharma process. You would have most likely concentration. For instance, let's say your medicinal product, if the final product spec is in terms of purity and concentration, most likely, because if it's not enough pure, okay, you will not be able to take them up. So eventually speaking, this is what is going to happen. So these specs, which are typically the production specs, right? Uh, so the so these production specs are very difficult to measure compared to other variables. So what are the other variables which are easy to measure? Which are, it could be flow, it could be temperature, it could be pressure, it could be um, so these are three: flow, temperature, and pressure are the typically variables which are easier to measure. And why? Because these sensors, so see, you have to look at how you implement this in the plant, right? These sensors are fairly easy to install. How do you sense something? You need a sensor. So sensor is basically, most likely, it would be an electrical transducer. So it takes up something and gives you something else by means of uh, uh, doing some, so for instance, if you're measuring temperature, most likely it would be RTD, resistance temperature device, okay, or it could be thermocouple, fine. And flow, it could be ventures, orifice meter. So you will learn about this a little bit more in the in your process control lab course or during the instrumentation course. So pressure generally done with the help of gauges, Gordon gauges. This is technically not really useful for what you call real-time measurement. Otherwise, what is known as DPT, which is differential pressure transmitter. So these sensors are fairly cheap. Because eventually this is material, and this and sensors are fairly cheap to install. So you have to look for a plant that contains thousands of components, thousands of lines, so on and so forth. Okay. So it could be fairly cheap and easy to install. Easy to install in the sense that it doesn't require a high supervision. You don't need to bring in a team to install it. Somebody who is reasonably proficient, you could do that. So that takes up the major chunk of the process, what you call process variables. But as we told, but they are not the production specific or the quality variables. Okay, so the production specific or quality variable, what would happen? So these are generally measured. So these are concentration, purity. This requires very specialized measurement. So these are mostly done with the help of chromatographic process. Okay, so it could be gas chromatography, liquid chromatography, or high performance liquid chromatography, and you might require something known as mass spectrometer to measure this. And these are mostly done by sampling, because so a distillation column might operate, maybe since there is a reboiler condenser, everything maybe operate above normal temperature, maybe 60 degree, 70 degree, or even 100 degree, who knows. Okay, and these kind of specialized analytical equipment, I hope you might have heard or at least seen in some of these some labs. Okay, these require very special care, maybe used in air conditioning. So these are very, very sensitive devices and extremely expensive, very, very expensive and very delicate as well. So it's difficult to make this both ends meet. So one requires real-time measurement, and that requires these components. Fine. That requires these components. Okay. Uh, but what would eventually is going to happen? How to connect these two? It's very difficult because you may not be able to place these devices directly on the floor because of its specialized operating conditions. So what people would do generally is take samples from field, in the sense that you have a sampling schedule previously prepared, which may be every 30 minutes once, or it could be 60 minutes once, depending upon the criticality of the operation. So this may be even 15 minutes once if it is highly critical. Anything below 15 minutes will be very difficult because this is done by manual sampling. Somebody has to go there and pick this up. And these instruments would be in the lab. And you take them and go there and do manually analyze. So what would happen? Let's say you are taking a sample at time 10 a.m. You really don't know. Uh, and and there is a lag, okay, because it has to taken to the lab, and you have to fire this in the instrument, for instance, GC, and or let's say GC is fairly fast. For instance, let's say it is high performance liquid chromatography. Then you need to set this up, sample you need to set up, you need to follow the protocol. This may I also, so let's say this lab from this is field. Okay, this is lab. So let's say lab to field because the lab would be somewhere in somewhere at some corner of your plant, and field maybe somewhere far away. Let's say it takes 10 minutes for them to bring the lab sample to the field to lab, and operation of the HPLC may also take around 10 minutes. So which essentially means that if you take the sample at 10 a.m., your result, okay, if everything if under very ideal conditions, your result would be available at 10:20 a.m. So what would happen? This is 10 a.m. You have taken the sample and you are getting the result at 10:20 a.m. 10:20 a.m. Let's say somebody wants to take a decision. So somebody is operating in the plant, which is an operator, or even an engineer, depending upon who is going to operate the plant. He really would like to know what is happening. So let's say if the distillate is giving poor results, he or she would have to do some fine tuning, which essentially means that he needs to play with this reflex ratio, and he probably need to fire up this reboiler little bit more for more vaporization, or even cut down the feed. Some decision may need to be taken in this middle. What to do? Because you don't have the information with you. So in those cases, this is fairly common in almost all the industries, large scale industry or even small scale industry. So they would have this historical data saved. So this is the concentration which is coming from, or purity which is coming from your HPLC, and you will have a lot of, but because they measured uh, and and this is would be most likely recorded in data historian, which the whole business is generally known as DCS, distributed control system. So, so this distributed control system contains almost every information, and it can extract it. So this would have a larger memory. It's like a cluster. You can assume that's a mini computer, and the control algorithms are mostly soft coded in DCS, and it can also save the data. So what people do is, okay, at the time t, for instance 10 a.m., you have pressure value, temperature, and 20 your concentration has come, but you will mark it at 10. Let's say 10:15, because there is so you have another data. Maybe 10:30 you have another data, and you would accumulate. I'm sorry. So these data is very similar to what we have learned also. You can model them. So and once you model, so for instance, you can model concentration as a function of pressure, temperature, and maybe the feed flow rate whatsoever. So what you can now do, so this is a soft model equation. This could be anything. This could be a linear regression, or even the neural network, or any machine learning model, like technically fully data driven. It could be support vector or whatsoever. And what you can do over here is, so you can get the concentration value, of course, predicted. I'll say use the word predicted, using the pressure value at the time t, the temperature value at the time t, and flow value at the time t, for instance. So you have to, once after this model is developed, so you can infer or predict the concentration by hinging upon some real-time measurement. These measurements are real-time. While this is an inferred variable, I mean, which is most likely possible because there are correlation between pressure, temperature, and concentration. Many of the time you'll be able to develop. Such developed models are called soft sensors. They are not hard sensor. Why? Because you are not measuring the concentration using a full-blown sensor by means of soft materials, which essentially the uh, inferred measurement as a function of other variables. So while these variables are measured hard by means of hard sensors, these variables are measured by means of soft sensors. Got it. So eventually what is going to happen is the following. So your models which are invariably developed will be either used for control, which we will see later, and we will also used for soft sensing, which is basically a detection. You identify for some variables as a function of others. So I think so. This is So what I really need to you need to really understand is soft sensing is a mechanism that is fully used in industry, which helps you to measure uh, which help you to kind of compute the variables which are difficult to measure using sensors. But eventually it would be measured by means of some lab analysis, and you tabulate those. And maybe what you could do is you keep on appending this list, maybe every once in a week or once in a month, you remodel. Why? Because you don't want, so if there is a bias, to avoid any bias, so your data list should be kept as new as possible, and you keep on developing the model. You keep on developing the model, and let's say you develop a model for a month, let's say for September, by means of data coming from, let's say, July, August. Okay. Then once the end of the September, you will develop a model for October. Maybe you yank out the July data because that seems to be sufficiently old, by adding September data into your pool. So this is, of course, for illustration purpose. You may have more months, maybe at least a year-long data or even more. So older data would keep on discarding, or newer data you keep on appending into the list, and finally you develop the model, and that could be used for soft sensing. Okay, the effect here is it is only computational. There is no hardware investment. So no hardware investment. And the lab sampling you have to do as part of the quality spec. So which this you cannot live with it, because this if you require approval. For instance, drug means you require FDA approval, or even other chemicals, or even food product, you have the registered body that requires their specifics to be approved. So which essentially requires a lab analysis data, which you cannot leave. So what are you now doing? Which you are using a lab analysis data, which was anyway you have to do to run your industry. You use them to use them for developing a soft sensor, and if there is a soft sensor working well, you don't need a hard sensor. So this is quite common. So this is another aspect of this modeling, is what I'm trying to say. Okay, so now, so till now, whatever we have learned is all our static model, which were slightly kind of orthogonal to the purpose of control. Control require dynamic model. That's why we started with ODE or PDE. But this vertical, of course, the static models are not really helpful. Static model in the sense that these data-driven models, for instance, linear regression. So how do you calculate linear regression output? Y as a function of a1x1 plus a2x2. So y, so again, if you put a timestamp on it, y at t is equal to a1 at x1 at t plus a2 at x2 at t. So that's why it is called inferential model. So based on the x1 at t and x2 at t, it infers what is the value of y, but it is not predicting. It is not using x1 of t value to predict y of t plus 1. Then it is the predictive model like ODE. So even the traditional neural net, okay, even least square linear regression, or even support vectors, or you might, hopefully you would learn these names at a later time, but I'm just throwing the names to you. These are traditionally used machine learning models. So they are all coming to their static category, which essentially means that you have to plug in the value of inputs at the time t to get the output at the time t. So what you really need in an industry is, this is good for inference. You don't need to predict, right? So for inferential cases, you don't need to predict. It's just as good as you may. So here what we are doing is predicting at t using, okay, attributes. You can use this word attributes. This attributes Am I audible now?
Yes, sir, you're audible.
Okay, so there is some problem with the Teams connectivity. So I hope you can see my screen too.
Yes, sir.
Okay, so yeah, so then what is the other solution? That's the point. So which essentially means that can we have a model that is dynamic also, and which can be used for control purpose. So inferential, you can regarding the inference, we have seen what we had to do, but for control require prediction ahead of time. So we have now we will just show some glimpse on some of those dynamic model. One is simply a discretized ODE. dy by dt is f of y comma u. U is your input that you are going to change, and this you can discretize, okay, which essentially means that yk minus 1 by delta t, which is corresponding to this dt, which is approximately equal to k minus 1 at value at y and u. So now you take this delta t over this side, yk is equal to yk minus 1 plus f of fy of k minus 1 and uk minus 1. So this is a recursive prediction mode. So now this, if you see, you supply the value of at yk minus 1, which essentially means that if you use the value of k minus 1 instant, you will get the value at k prediction. So technically speaking, there are two things. One is prediction and inference. So you have to be very clear about that. Prediction essentially means that you are getting a value at k plus 1, okay, using the values, okay, at k. So this is future. This is futuristic, looking ahead. While inference is this y of k is equal to a function of u of k. This is inference. So you are not, so this is instantaneous. So these are the two classes of model that you would see, and for control purpose, you need to know what would happen. What would happen when you inject something? Otherwise, there is no problem. There, you cannot take a decision, right? Okay, so this model is good for control. This type of models, because you are using the information at k minus 1th instant to predict something at kth instant. Okay, so now, so let's see some of the models that belonging to this type of. This is a very generic class of models. I'll use the word class. Okay. So let's see some of the models that belong to this particular category. One is known as auto-regressive exogenous input model, which is known as celebrated ARX models. So what does that do? Output here as a function of some previous outputs and also some previous inputs. So it is auto-regressive in the fact that your variable yk is depending upon the previous value of k. This is the auto-regressive part. It is regressed on itself. Okay. Here, this is the exogenous input part. So it is using some input. So this is one class of model that is used for control purpose. Because when you plug in, this is exactly like a differential equation. Okay, but this is a difference equation, you see. Difference equation. But very exactly like a differential equation. Okay, so the next type of models are called finite impulse response model, FIR model. Okay, so here out the model structure is slightly different. Your output at k plus 1, which is again futuristic, okay, is a function of your initial value and some historical value. So which is k minus n plus, starting from k minus n plus 1 to k. So when you put I is equal to 1 over here, it would be uk, and it is uk value ranges from uk to u of k minus n plus 1. So how much you need to check, that is, so here also you should know what is the value of n that you need to choose, what is the value of m that you need to choose. These are the model orders corresponding to the model order. There are ways to fix it. That's of course not currently under the scope of our interest. There are ways to figure out what is how much order you need to fix in, what is the previous, how many previous inputs you need to take, how many previous outputs you need to take, so on and so forth. So you can fix that, but assuming that they are fixed, So these are the model structure. So the take home message is that you have to, there are many of course, but at least for introduction purpose, you have to at least be cognizant that there are two classes, at least two classes of models. One is ARX models and finite impulse response model. And these models in general belonging to the category of time series model. So time series models essentially try to model everything as a function floating with respect to time. So t is a function of t minus 1, k is a function of k minus 1, so on and so forth. So let's say this is this. So here, how do you get this A, B, A? So I think internet slightly better now. Okay. Am I audible? I hope it is okay, I guess.
Yes, sir, you're audible.
Okay. Um, so how do you get, so the, what is the problem here? So what is in the linear regression? So you have to understand what is the problem, that in the linear regression, your problem is figuring out the coefficients A1, A2 such that your model, your original prediction is equal to, approximately equal to the actual prediction. So you are interested in finding coefficients A1, comma A2, etc. How do you do that? Least squares. You fit it. For ARX models, which is y at k plus 1, which is equal to, let me use the same notation. Okay, A1 at y of k plus, what is the n value? I think an. Okay, an at y of k minus n. Huh? Similarly, it is b1. Correct. So let's, you have b1 u of k plus bn u of k minus n. So here again, your what is the modeling problem? So these are modeling problem. You are interested in finding coefficients a1 to an, assuming n is fixed, it's given to you, and m is fixed, which is given to you, or you, there are ways to figure out that. Compute a1 to an as well as b1 to en, given, okay, a set of y, which is, let's say, y1. You have a table like this, y1 and u1. This is only you need. The rest you can make y1 to yn and u1 to un time. So this is at 10 maybe. This is 10 not 1, for instance. This may be so on and so forth. So you will have these numbers, and the model that you make would have, let's say it is y2. Let's say we are interested in ARX model of second order. So y2. So in fact, let's write it very generally. Yk plus 1 is equal to a1 times yk plus a2 times yk minus 1 plus b1 times uk plus b2 times uk minus 1. So from this data, you can fit this model to get this a1, a2, and b1, b2. So we are just leaving this aspect for now. I'm just saying how to do this. So similarly, for impulse response model, sorry. So impulse response model, your idea is, so see, what is the parameter here? Only one parameter, which is H. There is no A, B here, but you have H. The idea is to figure out what is that. That is the modeling problem. So the way you do it, you do a step test. Step test, how you know how to do it? You have an input, you step it up. Oftentimes your model would be giving your responses like this, whatever. This is y as a function of t. So this is exactly what is this. So you have your step response available. Okay. Then, of course, this is now figure out as, let's say this is the sample 1, this is sample 2, sample 3, so on and so forth. So you fix this delta t, which is the sampling time, and based on that you kind of segment the figure. So you drop a perpendicular from here to delta t, you drop a perpendicular from here, so on and so forth, go on. So this would give you this sort of a structure, and so impulse response is this point. See, these are the impulse responses. This stair height of the staircases. So one staircase is this, one staircase is this, so on and so forth. So how do you do it? How do you calculate it? Okay, it is simply, okay. So the point when you drop the perpendicular, let's say it is called as S1, S2, S3, so on and so forth. Okay. So how do you calculate S2? S2 is equal to SI, the total distance, which is sorry, H2, which is equal to total distance, which is S2 minus this particular, which is S1. And similarly, H1 is S1 minus S0. S0 can be 0 itself. So you could develop this. So these points are called step response points, and H is the impulse response point. So that is basically what we have done. So the model structure, let's say we are trying to develop a model worth three previous values, UK minus 1 and UK minus 2. Your coefficients that you need to compute as H1, H2 and H3, and H1 is S1 minus S0, H2 is S2 minus S1, H3 is S3 minus S2. Now, so you can just, of course, reorganize everything and write this as a function of S0, S1, and S3. So that is what we have done at a later time. It is S1 times UK minus U1, S2 times UK1 minus UK2, and S3 times UK2. So this is in terms of S, while this is in terms of H. So which essentially you can write these models as impulse response models and also step response models. I would say equivalent. I will not say same because your model would be slightly different. So while the step response model would have a coefficient h, your impulse response coefficient will have a coefficient h, while step response coefficient will have a coefficient s, because both of them are related. How? S1 is equal to H1 is equal to S2 minus S1. I'm sorry, I think H1 is equal to S1 minus S0. So with this, you can map S to H and H to S. So I think this is what I wanted to convey from the data-driven modeling perspective. And you can look at the book little bit, and it contains a bit more contents, I suppose. So where are we now? Okay, so just to do a quick recap. So So we have started from ODEs or PDEs, moved to transfer functions, and we have seen the complicated transfer functions like first order, second order, or even complex, which is more than complex than first and second order. Okay, and how to get this ODS and PE? That is first principle model based on mass, momentum, energy on a parallel track. Okay, we also saw data. Okay, and database models like linear regression. Okay, again fitting first order plus time delay, or even first order or even second order from data. Okay, and we have quickly saw what is how neural nets. We have seen now soft sensors, also ARX models and impulse response models. So this is fully data driven. It is the ML route to it. This is the classical first principle route to it. Okay, and now we kind of stop the dynamics part of our course. We have learned enough of the dynamics. Now, post this, we will see how these models could be used in control. So, process, dynamics, and control, right? So, this part is we kind of complete, and we will now embark on our control based on these dynamic models. So, in the subsequent classes, we will fully focus on using this dynamical model, most likely transfer functions. This is just given you a hint. So there is another parallel track that to the whole story, which we might not explore as part of this course. Maybe advanced process control. We'll consider this track a little bit more, and any course on machine learning would consider the modeling aspect of this. Any course on machine, of course, not first FOPDT and SOPDT, like neural network, so on and so forth. So this is the broader picture that I am giving you and where it is applicable. So any course on ML would only focus on this model development. We have given you a flavor because that is the eventual application, and we now have seen both the phases. We'll embark on the control, and if you really need to look at how these data driven models used in control, a good idea to look at the course on advanced process control. But being our scope, we will take maybe this to some extent. This I'm not very sure. Take it up to the control. And next 4 or 5 modules, of course, if time allows, we'll look at how do you do the control using this model. So what is the control problem? Okay, so we have seen U of t, in fact, as a function of y of t as a function of u of t. So what is the value of u I should give to reach? So every y, so this can be production specification like purity, concentration, anything. So let's say given your purity concentration y concentration, what is the value of u I should take, which is these are manipulated inputs, manipulated. How do you devise this manipulated input so that I can reach to this desired target, which is also called set point? So this is the next part of the course would be focusing upon. So what have we done? We have done the forward path, which is modeling y of t as a function of u of t. Okay, and the control is definitely taking the reverse path. Okay, which essentially means that, okay, so let me just draw it more carefully. So what we have done is this. We given y of t, what is the value? Given u of t, what is the value of t? This is modeling or simulation. When you give them, when you do the model, you will get this. And when you do control, or in fact, you also hear a word called optimization, which are they are closely related. In fact, control is in a large scale, in a large context, it is an optimization problem, which of course is again out of our scope to explain why control is an optimization. But here we are going to do this reverse. Given this y of t, given the y of t, how do what is the value of u of t? It's like a forward. This is forward, and this is the reverse. So modeling and control is has to be a cyclic process. The modeling would help you to predict, and control will help you to solve the inverse problem, or inverse or reverse, whatever you would like to call. Okay, so with this, so I don't want to take anything more at the moment. So we will stop at this moment. Okay, so we will not have our class on the coming Tuesday. And of course, this Monday, we don't have the tutorial because we have not covered enough. So we'll meet you all on the Wednesday, and we will start with the control aspect of it. Is that fine?
Sure, sure.
Okay, guys, then great. It's very close to 11. So I think I would like to close the class. So see you all on the coming Wednesday. Bye bye.
Sure, sure. Thanks. Bye.